Hi, in this presentation, I'm going to show you our newest development, the Galileo Hub, a prototype of a fully automated tissue microarray integrating artificial intelligence and deep learning-based techniques for precision tissue cell processing. Galileo Hub will also be able to reduce the time of tissue microarray production workflow. Our partners, Integrated Systems Engineering and Eubotica. Let's talk about our partners. Integrated Systems Engineering. Integrated Systems Engineering is a bioengineering company highly specialized in the design and development of biomedical instruments focused on the field of tissue microarray, TMA, technology. Our mission is to become one of the leaders in tissue microarray technology in the context of digital pathology. Our engineering team is highly skilled in robotics design, SW engineering, and customer support. Our Galileo TMA instruments are installed in cutting-edge hospitals and research centers worldwide: Europe, USA, Canada, Brazil, China, and Australia. Some examples would be the Mayo Clinic, MD Anderson Cancer Center, Mount Sinai, New York, or CHOP in Philadelphia. Eubotica. Eubotica Technologies provides technical expertise in the area of computer vision and machine learning in embedded systems at the edge. Eubotica is headquartered in Ireland with a team of AI engineers and also has a team of computer vision engineers in Spain. Eubotica has developed computer vision and machine learning algorithms for several different market segments, including space, LOT, 4.0 industry, and biomedical. Our mission is to develop AI models for different applications, including transform satellite services through onboard artificial intelligence. Let's talk about the current situation. Digital pathology incorporates the acquisition, management, sharing, and interpretation of pathological information, including slides and data, in a digital environment. Digital slides are created when glass slides are captured with a scanning device to provide a high-resolution digital image that can be viewed on a computer screen or mobile device. Because of their great natural heterogeneity, pathological structures have been challenging to detect with classical machine learning techniques. This is where a prototype comes into play. Galileo Hub combines artificial intelligence with tissue microarray technology. Integrating deep learning-based algorithms into digital pathology allows robust and reliable detection of structures. These algorithms identify rules from the underlying patterns in the image using examples instead of code. Deep learning capabilities can be easily combined with image analysis to get the best out of both worlds. Users can train their own algorithms from scratch, tailored to their need or use. Let's talk about tissue microarray technology, or TMA. TMA combines tens to hundreds of paraffin-embedded tissue specimens into a single paraffin block. It's possible to slice up to 200 consecutive sections of 4 to 5 micrometers from each TMA block, mounted on a microscope slide. The TMA slide can be processed like ordinary tissue sections with a wide range of techniques. Standard pathology methods of analysis: histostaining, immunohistochemistry, immunofluorescence, or FISH, but also innovative methods of analysis, 3D organoids and 3D spheroids. Let's talk about the integrated workflow. Starting by selecting the block tissues and the glass slides of your pathology archives. Introduce the tissue blocks using the template geometrical model of the Galileo Hub. In parallel, our system will automatically detect the tumor regions on the glass slide using AI techniques. The glass slide is also automatically registered to the block tissue, where the needle of the Galileo hub will select the tissue and all the cores to build the module and obtain as a result the TMA and the digital report. Let's watch a couple of videos with the AI process and with the entire process carried out by the Galileo hub. Starting from the whole slide image, the system automatically detects the tumor regions and creates a gray map image where the dark area shows those with higher probability of being malignant regions. Then, the block tissue image is also automatically registered to the glass slide image. First of all, you can see the superimposition of both images, and after applying the AI model for registration, a perfect match is obtained. The transform of the registration process is applied to the gray map image, which has the same size as the block tissue image. As you can see, the selected regions are similar to those detected in the glass slide image. Then, the tumor areas can be selected from the block tissue. The coordinates of the tumor areas on the block tissue are transferred to the Galileo hub system to select the course and build the entire TMA. Let's watch the second video.
It is a pleasure to introduce you the new Galileo Hub fully automated tissue microarray. Before starting the TMA construction, you need to select the core position. To do this, you need to import the glass slide from the AI suite, and then you need to select the cores in each spot, as you can see from the images. In alternative, you can do the core selection using the software of the Galileo, which allows you to pick up the core directly from a donor block which is previously marked by the pathologist, or using the glass slide positioned directly on the tissue block, or you can take an image of the glass slide and do the digital superimposition, or you can use a 3 points automatic matching of the tissue and glass slide image. At this point, we can look at the unique feature of our fully automated tissue microarray robotics mechanism. After the homing of the table, we check if the needles are bended or broken. Then we check the barcodes of the trays on the table and the barcodes of the tissue blocks. After that, we check the height of the paraffin of each block on the table. Now we are ready to start the automatic punching. The first step is to clean the recipient needle. The robotic arm will move the needle into the waste bin and cleans the needle. This is very important for functional of the needle and for cross-contamination. The robotic arm at this point will move the needles on the top of the recipient block and makes the hole in the paraffin. After making the hole in the paraffin, the robotic arm will rotate and will bring the donor needle on the top of the waste bin where it will be cleaned. After the cleaning of the donor needle, we are ready to pick up the tissue core from the tissue block, checking that the tissue core will be picked up and it is inside of the needle. The donor needle will move on the top of the TMA block and will insert the tissue core inside of the hole made previously by the recipient needle. The robotic arm will rotate and will bring the recipient needle on the top of the tissue block and will place the paraffin inside of the hole previously made. This sequence of operation will be repeated for each tissue cores which has to be made to create the tissue microarray block. This is the final result of your TMA construction block. We'd like to thank you for the attention. If you want to know more, please contact us.
Why is our innovation perfect to help users and fulfilling needs? Galileo Hub has the following unique features. It integrates artificial intelligence and deep learning algorithms to select the area of interest and match the tumor area with the tissue image. A fully automated tissue array with an open architecture which allows the use of different sizes of tissue blocks, standard, macro, and 96 to 384 microfuge plates. A sensor to detect if the punching needles are broken or bent. It detects if the tissue core was picked and placed into the TMA block. Value. The users of the Galileo Hub are pathologists, cancer research centers, including pharmaceutical companies working on biomarker development and validation, stem cells, and spheroids or organoids. Our users really appreciate the open architecture of our Galileo TMA instruments and the quality and readiness of our support service. With Galileo Hub, our users will get high quality and reliable instruments with the best service support. Market and competition. Potential reference market is artificial intelligence in digital pathology. The Galileo Hub will be the first TMA instrument which integrates artificial intelligence based on deep learning to automatically select the area of interest, matching the histological image slide with the image of the donor tissue. The competitors on the market are 3D Histech in Hungary, Estigen in Estonia, Everbio Taiwan, Unitma South Korea, and Alphalis in France. The Galileo Hub is the only TMA on the market with an open architecture and other technical features which differ from competition. Relation to DIGI-B-CUBE. EU funds like DIGI-B-CUBE contributed to the first stage of the Galileo Hub development and to the implementation of the AI based on deep learning for tumor detection and matching the tissue image with tumor area on the glass slide. The main pathology research institutes, Mayo Clinic, Mount Sinai in New York, INT, IEO, and others, are interested in fully automated tissue microarray instruments with integrated AI for tumor detection. We are also in dialogue with some investors interested in launching this technology into market. So, we've got this great idea. Now we need your help to make it come true. This is why we're looking for industrial and/or financial partners to bring the Galileo Hub with artificial intelligence and deep learning to the next level, placing it on the market. If you're interested in our technology and want to know more, please contact us for further information. Thank you for your attention.